Hi, my name is Daiki Miyagawa. I'm from Shizuoka University in Japan. Our research is based on evolutionary games on graphs with mobility. We use a special migration method which is called Lévy flight and study how adaptive migration of agents affect evolution of cooperation. First, although cooperation among individuals have been key to sustaining societies, evolutionary game theory has revealed that cooperators were not favored by natural selection than defectors. That's because defectors can exploit from cooperators as free riders. However, many previous works have revealed that special effects with mobility of individuals can promote the evolution of cooperation. Cooperators can survive together and make clusters of themselves like this. Okay, from now on, let me describe our model. It has two features in migration. The one is that our model uses Lévy flights as migration method. Lévy flight is a kind of random walk model. It is composed of many small movements with a few big movements, like this trajectory of movements. More formally, lengths of movements in Lévy flight follow power law distribution. Another one is sensitivity to defectors, which affects the decision whether jump to another side or stay here. If the agents have high sensitivity, they want to jump even if there is few defectors around it. In contrast, the agents who have low sensitivity decide to stay there even if surrounded by defectors. Next, I'll show you the simulation process of our model. At first, the program chooses focal agent randomly. Second, the focal agent and its neighbors play games with their neighbors. At that time, they use this payoff matrix with payoff parameters S and T. Now the cumulative payoffs are like this. Next, the focal agent imitates the strategy of the neighbor that obtains the highest payoff within the neighbors, including itself. At the last, the focal agent decides to whether jump or stay using sensitivity parameter S and the fraction of defectors within its neighbors. The condition where the focal agent decides to jump is this one. This term means the fraction of defectors within its neighbors. So, if this value is less than parameter S, the focal agent performs the Lévy flight, but otherwise, it stays here. Intuitively, the higher S the agents have, the more aggressive to jump to another side the agents are. This is the animation of evolutionary dynamics of our model. We can see that cooperators denoted by blue sides can make clusters and survive. This color map is one of our results. This shows how cooperation evolved in the whole TS plane. The color indicates the fraction of cooperators at the end of simulation. The plane is separated by the types of games like this figure. To investigate the optimal sensitivity, we increased S from 0 up to 1 by 1/8, focused on Prisoner's Gemma game and Hawk Dove game. In this region, the fraction of cooperation changed as S increased. We also summed up the fraction of cooperators overall of ST plane for each S values and plotted them. This shows the moderate S most promoted cooperation. Next, we investigated the dependencies of the optimal sensitivities on density of agents. We changed the densities like this. The obtained figure is this. As the density becomes larger, high sensitivities to defectors work better for cooperators. That's because agents in the high density rarely succeed to find empty side to jump unless the sensitivity becomes high. Okay, I'm showing a summary. Our poster has extra information such as detailed description of model and another result comparing to non-power low flight. Please check it out and come to my poster session. Thank you for watching and have a nice conference.